Ever wondered how scientists determine if two groups of data, like people, plants, or galaxies, are truly part of the same cluster or completely separate? Today, we're exploring a groundbreaking statistical method that's revolutionizing how we analyze data and why it's changing the game for clustering. Let's start with the basics. Imagine you're analyzing a dataset with thousands of data points, maybe customer purchase records, genetic sequences, or images of celestial objects. You suspect there are hidden groups within this data, but how do you prove those groups are statistically distinct? This is the core challenge of clustering, the process of identifying naturally occurring groupings in data. But traditional methods often struggle to distinguish between meaningful clusters and random noise. Enter the boundary test for cluster ties, or BTCT, a novel approach developed by researchers to address this gap. Here's how it works. First, the algorithm identifies boundary points, data points that lie on the edge between two potential clusters. These are the critical junctures, where the line between groups might be blurry. For each boundary point, BTCT examines its 7 nearest neighbors. If most of those neighbors belong to the same group, it suggests the two clusters are actually part of a larger unified group. But if the neighbors are predominantly from one cluster, that's a strong signal the groups are distinct. The brilliance of BTCT lies in its statistical foundation. It operates under the null hypothesis that the two groups are identical. Under this assumption, the probability of finding, say, 7 neighbors from the same group is analogous to flipping a fair coin 7 times. The chance of getting 7 heads in a row. Just 0.78%. In their experiments, researchers observed this rare event in some datasets, yielding p-values as low as 0.0078, far below the conventional 5% threshold for rejecting the null hypothesis. This means they confidently concluded those clusters weren't just random variations, but truly separate. But here's the twist. When tested on real-world data, like customer behavior patterns or biological samples, traditional methods like maximum mean discrepancy, MMD, and energy tests often failed. They produced false positives, claiming clusters were distinct when they were. BTCT, however, delivered remarkable accuracy, 89.9% on synthetic datasets and 78.9% on real-world examples. This precision stems from its focus on boundary dynamics rather than global distributional differences. What does this mean for data science? BTCT isn't just another clustering tool. It's a rigorous framework for validating cluster integrity. By focusing on local neighborhood structures, it avoids the pitfalls of methods that overfit to noise or misinterpret high-dimensional patterns. Whether you're analyzing gene expression data, social network communities, or climate trends, BTCT offers a more reliable way to separate signal from randomness. Next time you encounter the term cluster in a research paper or dataset, remember, it's not just about visual patterns. It's about statistical confidence. Tools like BTCT empower us to ask the right questions and avoid costly errors in interpretation. Thanks for watching. If you want to dive deeper into how BTCT mathematically formalizes cluster boundaries, check the links in the description. And don't forget to subscribe for more explorations into the cutting edge of data science. Until next time, keep questioning, keep analyzing, and keep uncovering the hidden structures in the data around us.